we're going to be taking the inverse of a 2 by 2 matrix, not a 3 by 3, just a 2 by 2. And this is essentially what we want to have down. I will highlight it down here. Basically this. And I wouldn't even worry about this because you know what a determinant is. I would write down a to the negative first, which is the inverse of a, equals, and then I would focus on this guy right here. So some matrices do not have inverses, right? The one that would not let us have an inverse is if the determinant of the matrix was 0, because then here we would be dividing by 0, which we can't have, right? And I'll just give a second for us to write these on. So essentially to find the inverse, you find the determinant, and then you multiply the matrix by the reciprocal of the determinant. But what you do to the matrix is you flip A and D and then make B and C negative. Which again, it might start to feel maybe overwhelming of like, okay, to find a determinant, I multiply these two and then subtract multiplication by the other two. And then this one, it has a weird thing where these are flipped and these are negative, but not flips. And I just got to say that, the more you work with it, the more delta math examples you do, you'll get it pretty quickly. All right. So flip them, negative, flip them, negative. And part of the way that I remember that these are the ones that are negative and not flipped is when you take a determinant, you subtract what you get when you multiply these two. So that's how I remember that those are negative, right? And then these ones stay positive but are flipped. And the reason that happens is essentially just if you were to work out how to get an inverse of a matrix like backwards, right? If you were to start and say, okay, how do I take, or if you do it generally, like how do I take this matrix? What do I multiply this matrix by to get an inverse matrix? And this is what it would be if you kind of like reverse engineered it, right? So it's not just poof out of nowhere. That's just what it is. Okay. So once you know that, I mean, these aren't that bad, right? So if we want to find the inverse, we know that the inverse is 1 over the determinant. Well, the determinant is 7 times negative 1, which is negative 7, minus a negative is going to be plus 5 times 2 is 10, 3. So 1/3 times, and then it wants us to switch these two and then make these ones a negative. Negative 5 would be positive 5. And so then your inverse matrix would simply be negative 1/3, negative 2/3, 5/3, and 7/3. And that shouldn't be that bad. I'll give it a second in case anyone's writing that down because we only have a couple examples to go through. And then, if you wanted to test if these were inverses, you would just have to multiply these together and you better get the identity matrix, right? All right. So our next one here, same thing. To find the inverse matrix of B, we need to do 1 over the determinant of B, which the determinant of B is going to be 3 times negative 4, which is negative 12, minus 7, which is negative 19, right? minus 7 times 1. So negative 1/19 times the matrix. We flip these two numbers, and then we make the other ones the opposite sign. Easy enough. Negative 1/19 times negative 4 is going to be positive 4/19. Right, positive 7/19, positive 1/19, and negative 3/19. Now I'll give a second to write that one down. And of course, simplify if you can, but in this case, we cannot. Right. Lastly, we have to do C inverse, which is going to be 1 over the determinant of C. Negative 8 times 9 is going to be negative 72, minus a negative 12 times 6. 6 times 10 is 60, times 2 is 12, is going to be 72. And the determinant is 0. And when you divide by 0, you like start World War III or something. You can't do that, right? That's illegal. So there is no inverse. Right? You can only have an inverse if the determinant is not 0. So that one's that easy. As soon as you found the determinant, you knew that this one can't have an inverse.